Start. Hello everyone. Our today's topic is number theory also, and we would be starting on that. Yesterday I taught about the primality check and other things, and binary exponentiation. I hope you all are clear with it. Anyone has any doubt in that? Okay, so let's move on. So today's contents are the number of divisors, sum of divisors, and extended Euclidean algorithm, linear Diophantine equations, and Lucas theorem, modulo inverse. So what the question comes is, what are the number of divisors of a given number if the prime factorization of that number is given? I guess you guys studied that in JE, so please answer.
Summation of powers pi plus 1.
Actually, that's not summation. I guess that's multiplication. Multiplication of powers plus 1. Yeah, product of powers plus 1. So the number of divisors are product of powers plus 1, and how that formula comes everyone knows, I guess. Yeah, so P and C. Yeah, so there is one more property about number of divisors, that if two numbers are coprime A and B, then number of divisors of AB is equal to number of divisors of A into number of divisors of B. I guess that's clear by this formula. Clear? Why? Yeah, so coming on to the sum of divisors. So what's the sum of divisors if prime factorization is given? Yeah, formula is given, but still how it comes, anyone?
You just write down all the 1 plus p1 square p1 plus p2 square plus p3 square. Sorry, p1 square p1 cube, p1 ka power 4, p1 ka power 5, and then multiply with 1 plus p2 power 2. So this will give the sum of all, the multiplication will give the sum of all the factors.
Yeah, that's correct. And that GP sum is represented as P power plus 1 and that. So what Abhinav said was that let's say the presentation was P1 power E1 plus into P2 power E2 into P3 power E3. So we calculate the sum of divisors by 1 plus P1 plus P1 power P1 square till P1 power E1 multiplied by 1 plus P2 square till P2 power E2 and so on. So that will give if we expand all those brackets, that will give the summation of all factors. Any doubt in that? Yeah, so let me demonstrate. Yeah. So let's say I want to find the sum of factors of, let's say 2 square into 3 cube into 5 power 2, 5 square. So that would involve all of factors like, that's basically summation 2 power I, 3 power j, 5 power k, such that I less than equal to 2, j less than equal to 3, and k less than equal to 2. Right? So these, as I, j, k are independent, so we can like split the sigma. So that's sigma 2 power I into sigma 3 power j into sigma 5 power k, that's 5 actually, into sigma 5 power k. Right? So these individually are GPs, and we can sum it, so we get the formula of P1 power E1 plus 1 minus 1 upon P1 minus 1, and product of all these. Is that clear? Okay. So, yeah. So again, the sum of divisors property, like we can do these in case of coprime numbers, like sum of divisors of, like, let me demonstrate only here. let me denote sum of divisors by sigma, let's say. So sigma of n, let's say, is the sum of divisors of n. So sigma a into b equals sigma a into sigma b if a and b are coprime. So basically in factors, whenever we want to sum something over factors, so we generally use this property. This property just doesn't hold for number of divisors of sum of divisors, it holds for many other functions also. That if a and b are coprime, then the function of a into b is function of a into function of b. So we use this property and we just calculate the function for powers of prime and just multiply it according to the prime factorization of the number. So we get the answer. Yeah, so extended Euclidean theorem. Yesterday I taught about Fermat's little theorem, about that a power p minus 1 is equivalent to 1 mod p. Yes. So what Fermat's theorem says is a power p minus 1 if a p doesn't divide a and p is prime. That's what Fermat's theorem says. Yesterday I guess I taught this. So everyone is clear with this now? So what extended Euclidean theorem says is if this just basically gives us modulus for primes. What if the number which we are taking mod from is not prime? Then what would we do? So that's what extended Euclidean theorem is about. So extended Euclidean theorem says that for any number n and a, yeah, basically if I just put these brackets, these basically denote GCD. That's a mathematical symbol. I hope if anyone is not clear, I tell it here. So that's representing GCD if I write bracket and two numbers. Okay. So a power phi n is the Euler-Taussian function. So a power phi n is equivalent to 1 modulo n. So if we take power phi of n for any number n, and if a and n are coprime, then a power phi n gives modulo as 1. So that's a pretty useful property when modulus are not prime. We can calculate modulus by this theorem. And modular inverses can be also calculated with the help of this. Like we can write A inverse is equivalent to A power phi n minus 2. Oh sorry, phi n minus 1, my bad. And we can verify that if n is prime, this just gives the Fermat's little theorem. Because phi of prime is prime minus 1. So I guess no doubts in this. Or should I give an example?
कैसे आया वो? A raised to power
I
5.
like, yeah. Proof is like अभी बाहर चला जाएगा थोड़ा लेवल के. Online you can read if you have interest. Like अभी यहाँ थोड़ा irrelevant हो जाएगा and CP में ज़्यादा यूज़ नहीं होता. So yeah, so let's consider the Diophantine equation, linear Diophantine equation. No, wait a sec. ax plus by is equal to c, where a, b and c are natural numbers. So when will the solution of this exist? Like x and y belongs to integers, those are unknowns. So given a, b and c, you have to tell whether some x, y integers exist that satisfy this equation. How do you do that? Like when will the solution exist? No, it's not system, it's just one equation and the criteria is ABC are natural and XY are integers, not real numbers.
C minus B by लेंगे
Okay.
and then we like we need to prove that there exists a y such that C minus By is 0 modulo x.
Modulo A, yeah.
Modulo
A and B are given, X and Y are variables.
A.
Yeah.
C minus By is 0 modulo A. We need to just solve that. So we can use B inverse.
Okay.
And
So Y is equal to C into B inverse. Okay, that's B inverse in modulo A. Yeah, that can be done. Yeah, so what he said was we would do like this, AX is equal to C minus BY. And now what we can do is, we can say that C minus BY is equivalent to 0 mod A, if such solution exists. And through this we can do just Y is equal to C into B inverse. So if we put Y equal to C into, mod X, yeah, so if we put Y equal to C into B inverse, yeah, so this would convert into C minus B into C B inverse, and B inverse is modulo A. And if we take this mod by A, and if we take this equation whole mod A, then it would be equal to 0, it can be seen. B into B inverse would be equivalent to 1. But B inverse exists only if A and B are coprime. So what would be the general case if A and B are not coprime? What would be the conditions on C?
C should be divisible by the GCD of A. Multiple of GCD of A.
Yeah, that's correct. So if C is divisible by GCD AB, then we can say this equation has a solution. And the proof of that is quite simple. Let me do that. So, proving that we know that AX plus BY equal to C must have a solution. So, if we know AX would be divisible by GCD AB and BY would also be divisible by GCD A comma B, because A and B both are divisible. So, C should be divisible by GCD AB should divide C. That is a necessary condition. Right? But how is it sufficient? So let's say C is some multiple of GCD AB. So AX plus BY is equal to K into GCD AB. Sorry about the handwriting. Sorry about the handwriting. And by extended Euclidean theorem, we know that there always exists x comma y such that this is satisfied. We did this in 10th class, first chapter. Like we calculated the remainders and by long division we substituted the values. Like for example, if I want to find, Yeah, if I want to find the GCD of, let's say, 12 and 17, what we did is we wrote 12, ouch. Yeah, 17 is equal to 12 into 1 plus 5. And then we wrote 12 equal to 5 into 2 plus 2. And then 5 equals 2 into 2 plus 1. And then 2 is equal to 1 into 2 plus 0. So 1 is the GCD, right? So if we substitute 2 through the above equation, and then we substitute 5 by this above equation, then we substitute 12 by this above equation, then we will get something like from a into 17 plus b into 12 is equal to 0, equal to 1, sorry. We can always do this, right? If we substitute the values, we will get some integers a and b, if we keep substituting, right? Any doubts? Okay, let me calculate the a and b only here. So I write 2 as 5 minus 1. Wait, sorry. From us, let me write 5 as 17 minus 12 from here. So I can write 12 equals to 17 minus 12 into 2 plus 2, right? And now 12 is written like this, and now 2 can be written as, wait a second, I guess I messed up a little bit. Yeah, so 2 can be now written as 17, so 12 minus 17 minus, which is equal to 3 into 12 minus 2 into 17. This is okay? Now if we go through this equation and again substitute the value of 2 and 5, wait. Yeah, I go on this equation and substitute the value of 5 and 2 both. So 5 is 17 minus 12 is equal to 2 into 3 into 12 minus 2 into 17 plus 1. 1 is equal to 17 minus 12 minus 6 into 12 plus 4 into 17. So 5 into 17 minus 7 into 12 is equal to 1. So we get a is equal to 5 and b is equal to minus 7. Clear? So we can always find ab like by substituting these. So GCD a comma b can always be written as ax plus by, where x and y are integers. So now if C is divisible by GCD AB, okay, sorry. So we write C as K into GCD AB. Wait a second. So this has a solution. Let's say the solution is x naught and y naught. Okay. So now we can write K into GCD AB. Now for K into GCD AB, we can say that K into x naught and K into y naught would be solutions, right? So we can say that there always exists a solution if these conditions are satisfied. That it is sufficient and necessary. It is necessary that we proved, and sufficient also by this we can say, right? Yes, okay. Anyone was noting, or can I erase? Sorry about that. So anyone wants to note can note, or else I will erase. Noted? Okay, great. Yeah. Yeah, so the algorithm for finding x comma y that I wrote is actually quite useful in finding inverses also. Like, I'll tell you that in the next slide. Yeah, so this is a code of finding those x and y coefficients. How would we find that ax plus by if is it equal to GCD AB, then what would be the coefficients x and y? So in this code, just if b is equal to 0, then we say x is like 1. The GCD is a, right? GCD of a comma 0 is a. We define that. So if like b is 0, then we say the GCD is a into 1 plus b into 0, right? Correct? So we return the GCD as a, and the x and y are respectively 1 and 0. Now we declare two integers x1 and y1, and we say d, let's say, is the GCD of b and a mod b, right? So we know that GCD a comma b is equal to GCD b a mod b. Yesterday I told that how to find the GCD by Euclidean method. So we are just doing this all to find the respective coefficients. So if we find the coefficients for b and a mod b, like we say that if we say that GCD a comma b is equal to x1 into a into b, plus y1 into a mod b. A mod b. So anybody tell that what would be the coefficients of x and y if you want to write this? Like, can we write x and y in terms of x1 and y1? Sorry?
Like x would be equals to y1 and y would be equal to ax1 minus a by b into y1.
Sorry, y would be equal to?
Ax1 minus a by b into y1.
Okay. That's correct. So the basic idea was to replace a mod b by a minus a by b into a into b,
Yeah.
right? Yeah. So that's correct. So the basic idea here is, I don't know the exact expression. Yeah, but idea is that only. Idea is we replace what is basically mod. It's basically subtracting the highest multiple of a that is less than equal to b, right? So we replace a mod b by a minus a by b greatest integer into b, right? So we replace a mod b by this, and then we will get the answer, and I guess this is correct. Yeah, that's correct. Yeah, so in the code also, I have written like that only. So we first compute the x1 and y1 for b and a mod b, and then we declare x as y1 and y as x1 minus y1 into a by b. So it gives us a recursive algorithm. Everyone okay with this?
Can you explain again?
Okay, I'll explain it.
Not the code.
The code, okay.
Not like code.
Achha, okay. So basically, a mod b wala part. So basically what I said is a mod b is subtracting the largest multiple of b less than equal to a from a, right? So we can write a mod b as a minus a by b into b. So if we replace in that and above equation and compare those two equations equating x and y coefficients, then we will get this answer, x equal to y1. Should I equate? Okay, let me do it. So we would be replacing this by GCD a comma b is equal to x1b plus y1 into a minus a by b into b, and this is obviously integer. So now we can write it as GCD a comma b is equal to ay1 minus b into x1 sorry minus b into right? Is this okay? So we get we replace this negative sign by plus, so ay1 plus b into x1 minus a by b by 1. So x is y1 and y is this x1 minus a by b by 1. Alright. So this gives us a recursive algorithm to find the coefficients x and y in the equation ax plus by equal to GCD AB. So this code is clear. Just implemented the algorithm. Yeah. So in this case also, for finding ax plus by equal to c, for finding the solutions of these, what would we do? For finding x and y. Yeah, correct. So we would first divide c by GCD AB and then multiply, we would first calculate x and y for GCD AB and then multiply them with the coefficient c by GCD AB, right? So we would get the answer. And if we get something like that, for how do we find like all solution? Could you find the general form of all solutions for ax plus by equal to c? Like we would find a solution from that method. Can you find like all? How would we find all or some basically multiple solutions.
We have multiple solutions.
Yeah.
GCD will have unique solution, or it will also have multiple solutions.
It will also have multiple. It finds one. Euler, extended Euler's algorithm finds one. For GCD also we have multiple solutions. Like in AX plus BY, if I find a solution, let me explain with writing only. Like for AX plus BY equal to C is a solution, let's say. Then A into X minus B plus B into Y plus A is also a solution, na? Like X naught, Y naught, let's say, X, Y variables. So this is also a solution, no? Yeah, so could we find the general solution, well, like in form, closed form, like all solutions, X and Y, for a specific given C? I guess this expression gives a lot of hint.
X naught minus BT and Y naught plus AT.
Sorry?
X naught minus
X naught minus LCM of B into LCM of AB.
Sorry. Yeah, A into X naught minus. Sorry.
LCM of AB.
LCM maybe. Okay. Like it would be fine, just tell me how to find like infinite number of solutions. It won't be like if all.
Into GCD of AB.
Sorry, A into?
X naught
Hmm.
LCM AB upon A
Okay, minus.
minus LCM AB upon A.
Okay.
Multiple of LCM AB upon A into T.
Okay. Plus B into?
X, Y naught minus LCM AB upon B.
I guess plus you want to say, right? Yeah. Upon B. Yeah, that is correct. Yeah, so, sorry. So we can also write LCM AB upon A as B by GCD AB. Yeah, that's right. So as LCM AB is AB by GCD AB, right? And if we divide that whole by A, A would get cancelled, and this is B by GCD AB. Yeah. Yeah. So for all the solutions we have A into X naught minus T into B by GCD AB plus B into Y naught plus T into A upon GCD AB. So for putting different values of T, we would get different values of these coefficients basically for some C. If we find our X naught, Y naught and we apply this, then we would get all the solutions, all the possible solutions for some value of T. Like if there is any solution, there will exist a value of T which satisfies this.
T can be
Yeah, t can be any integer. Integer. If t is a real number, then we can do anything, right? Yeah, so t is any integer. Yeah, could be negative also, like integer. So here is a practice problem. Okay. Yeah. Oh. So try this problem. Oh.
What is the question? Given a natural number and please output summation of all
Yes, I.
of its proper divisors.
So the problem says is given a natural number and you have to print all its divisors. And sorry. Yeah. So give me a solution.
Actually, we can like go from 1 to square root of n, and we will check
Yeah.
if
Yeah, we can do that, but the test cases given here are quite high. Yeah, that is correct, basically, but it would require a bit more time.
square.
Basically, what she said was we would define, let's say, a function for sum of divisors of n, then we would go from 1 to square root of n. And if we find the divisor d, then we add d and n by d, right?
Yeah.
Yeah, that is correct, but it would take a bit more time, like slightly more than time limit. Yeah, calculating prime factorization also takes root n time. So if we go, like actually the test cases are given quite a bit. So if we go test cases into root n time also, that would cause a problem. So any like any guesses how do you do that? Try this for 2 minutes, then after that I'll give you a hint. The font size is clear, no? Yeah.
each number we will calculate the least prime factor
Okay, and then?
and then calculate all the prime factors.
Okay, right. And
We will put the values of each prime like value of prime factor and its power in the formula.
and how do we compute least prime factor? Yeah, basically you are right. Yeah. So basically, how do we do that is we apply sieve yesterday. In yesterday's I taught sieve. So by applying sieve, we can even directly calculate the sum of factors also. Like we go on a number and on its multiples, add that number. So that would take a complexity of overall n log n, where n is here given about I guess 5 lakhs. 5 lakh it is. Yeah, 5 lakhs. So n log n would work there. So we would apply sieve normally, or what Abhinav said, we can also apply the sieve for least prime factor and then calculate the prime factorization whenever a number comes, and by the formula of known prime factorization we will calculate the sum of divisors.
What would be the time? Then yeah.
Sorry? Why that would go test case into root n time now? Log n is less than root n now.
N log n is
So that's t root n. That's not. Now we can query the answer in O1 now.
acha, okay.
So that's n log n plus t. So that's better than t root n. So clear? Okay, great. Yeah, so question comes, how can we find the modulo inverse using the extended Euclidean algorithm? So, give me some solutions. Like how can we calculate the modulo inverse without applying the like extended Euclidean theorem of phi n? How can we do that? Like we know that phi n, a power phi n minus 1 gives that, but other than that, how can we find it?
Suppose if we want to, we will take modulo m.
Yeah. लिखा हुआ है वैसे.
तो basically वो a inverse x हो जाएगा, dx congruent to 1.
Yeah. Correct. ठीक है. So basically we find those x and y where ax, if a and like we want to find, let's say, we want to basically find for some given integer a, we want to find an integer b such that ab is equivalent to 1 mod n. Right? That's the problem, no? So we can write it as we have to find some integer b such that this is equal to k into n minus 1 for some integer k. Right? And basically n into x I should write. Sorry, ouch, sorry. So k into, sorry, n into x, sorry about that. So n into x minus 1 for some integer x, right?
Okay.
Oh yeah, sorry, plus 1, sorry about that. So we have to calculate this, right? So what we can do now is take the nx opposite side. So a into b, b is variable here, minus n into x is equal to 1. So that's the linear Diophantine equation we solved. earlier, right? So if the GCD of a comma n is not equal to 1, so no solution exists, right? And if the GCD is 1, then we calculate the coefficients b and x by the extended Euclidean algorithm. And the first coefficient gives the modular inverse of A. So, and if in case, no, that's correct only, so leave it. Yeah, so here it's given that G basically is the GCD of A and M, the modulo. And if G is not equal to 1, then there exists no solution. Like we can't find the inverse. And else we calculate, and this is the given expression. Yeah, so that is actually x only, but if x is negative, then we go plus m and or do all that. So in order to make that positive, like for finding multiple solutions, we did plus b one side and minus a the other side. That's what the else part is doing. Yeah, so here are some problems. So you are given some numbers and you have to calculate the product of the difference of each.
Can you
So-
increase the font size, please?
Sorry? Font sizing. Better now?
Yeah.
So you are given some arrays, you have to calculate the product of each pair of differences. So go ahead and try with it. Just see the constraints also, like don't just see the problem only, because there are many things hidden in constraints to for the idea to solve the problem. Sorry? No, not necessarily distinct. Like you can assume, like if it's not, then the answer is 0, right?
N is like much bigger than the modulo. So
Yeah.
must be like two numbers which are
Hmm.
एक ही से में आ रहा है, तो डिफरेंस जीरो हो जाएगा.
Yep.
तो इस प्रोडक्ट जीरो आ जाएगा.
Hmm.
ये जीरो आना चाहिए मेरे ख्याल से.
Yeah. Hmm.
अगर 1000 से बड़ा हो गया.
Yeah. Correct. So everyone got what he said. He just basically said that n is quite bigger than m here in the given problem. So if n is greater than m, so everybody of you have studied pigeonhole principle?
Yeah.
Everyone knows, or should I tell? बता दो. Okay, बता दो. Okay. So what pigeonhole principle says is, like I can tell verbally only. So if there are n plus 1 pigeons and they want to pass through n holes, then there would be at least one hole through which at more than one pigeons passed. Sorry? So n plus 1 pigeon, n holes, there exists at least one hole from which more than one pigeons passed. Right? That's common sense, I guess. But it's quite of use here. So if we consider here n for this problem, n greater than m. If n is greater than m, then what we can do is, first let's calculate ai mod m for each ai. Okay? So now if we calculate ai mod m for each ai, sorry. So if we calculate ai mod m for each ai and any of the two mods is same, then the answer is 0, right? If ai mod m equal to aj mod m,
Yeah.
then ai minus aj mod m is 0,
0. Yeah.
right?
Yeah.
So if any two of the mods are same, our answer is 0. And by pigeonhole principle, if n is greater than m, then ai mod m only has values 0 to m minus 1. Right?
Yeah.
Mod m can be either 0, 1 to m minus 1 only. So if the n is greater than m, so we can consider each number as a pigeon and these are holes. So any one of the mods should have greater than 2 occurrences, right? So if n is greater than m, then our answer is straight up 0. So Samip, what would be the case if n is less than m? Yeah, so if n less than m, then we just brute force, because m is given quite small. It's 1000 only, so we can apply m square, right? So if n is less than m, we just brute force. Yep. So any doubts? Clear? Ouch. So here is the second problem. Please try it. Oh, font size. Samip, where are you? Okay. ठीक है याद है ठीक है Sorry?
We find the maximum power of 5.
Oh.
But it's not.
Yeah, that works in factorial, but not here, I guess. That's f into n into fn minus 2, not fn minus 1.
Maximum power of 5 and subtract the maximum power of 10.
Subtract. Why would that work?
तो जितनी बार 5 के मल्टीपल्स आए और उसके बाद 10 जो है वो नहीं आ रहे, मतलब 2 और 5 कॉमन आ रहे।
फिर से बोलिए.
n odd होगा तो 0 आएगा ही नहीं.
क्यों?
सारे वो और हो जाएंगे।
Correct. So there is no power of 2 in them. So you can't have 0. And what if n is even?
तो 2 की पावर मतलब वो
Maximum in give.
n by 2 का फैक्टोरियल के 0 फाइंड करेंगे।
Yeah, that's correct. So basically powers of 10 only, because 5, we can't get an odd multiple of 5 as a power. So we just calculate how much power of 10 it is. Yeah, that's correct. Yeah, so what we will do here is we find fn. Fn is basically n minus 2, n minus 4, right?
Yeah.
Till 1 or 2, whatever. So, wait. Yeah, okay. So, what we do here is, if n is odd, then we can't get a power of 2.
Yeah.
Because n minus 2, all of them are odd. So, we can't even get a single power of 2, so we can't have a 0 at the end.
Yeah.
So, if... Ouch. What the heck? बैटरी लो है, छोड़.
USB port.
Okay. अबे भाई क्या कर रहा है? इसका हुआ तो. अबे यार, एक काम कर, वहाँ से कनेक्ट कर सकता, यहाँ पे इस टेबल पे, और चेयर पर नहीं, यहाँ रख, टेबल पर रख सकते हैं इसको नहीं. Yeah, and screen share का देख ले एक बार. So let me explain verbally only right now. So if n is even now, so we will calculate how much powers of 5 are coming in it. or basically how much powers of 10 are coming in it, because the number of leading zeros is how much power of 10 by is divisible. So we will, if it is even, we would only get powers of 10 as 10, 20, 30 and so on. So we will divide n by 10, then n by 100, I guess. Wait. Yeah. So we can write that as 2 power n by 2 into n by 2 factorial, right? And we will calculate the power of 5 in n by 2 factorial. So that's correct. क्या? हाँ ठीक है. Sure अच्छा. देख लेता हूँ. हाँ ठीक है. So we will write that as 2 power n by 2 into n by 2 factorial, and I guess everyone knows how to find. Let me elaborate on like that only. So mic की दिक्कत है.
दूसरा माइक दे देना.
Connected है क्या दोनों? Connected है दोनों? अरे भाई फिर से बंद हो गया. So for a hello, are you yours? So for a given number n and a given prime number p, how do we find the order of p in n factorial? Basically, order of p is largest power of p dividing n factorial. Like what's the power of p if we do the prime factorization of n factorial? What's the power of p in it basically? So please find it, or if anyone knows the answer, tell it. Yeah. Yeah. Yeah, correct. So there are n by p numbers which are divisible by p. So they would contribute a factor of p plus n by p square. If I would do. So that would contribute a factor of 2, but once we have already considered them in n by p, so extra they will contribute 1, right? Similarly till n by p cube and so on till this number is 0. So this is the order of p in n factorial, right? So we will just calculate the order of 5 in n by 2 factorial for that problem, right? By this summation thing, right? Yeah, so moving on to the next problem. So font size is okay, or should I increase? Okay. Okay. And okay, the constraints are given, and here it's given. Yep. Sorry,
सी जैसा बना दे,
C जैसा क्या?
हर एक प्राइम पे से रिपीट होगा,
Yep.
वो प्राइम फाइंड करके
हम्म.
उसके आगे वाले नंबर्स पे वो मल्टीपल्स पे वो नंबर ऑफ फैक्टर्स मल्टीप्लाई कर देंगे।
उसके मल्टीपल्स पे,
मल्टीपल्स पे नहीं,
उसके आगे वाले नंबर्स पे, दैट वुड बी n स्क्वायर ना, log n नहीं रहेगा ना.
We just calculate power of each prime.
Okay.
प्राइम की सीव बना देता है,
Yep.
और फिर जितने भी प्राइम नंबर्स है उनका ये बेसिकली 1 प्लस 1 अपॉन e प्लस 1 अपॉन ये एक नंबर n से वो एक्चुअल नंबर्स मल्टीप्लाई कर देंगे।
Yeah, so basically what you're saying is order of p we would calculate. Yeah, that's the solution. For each prime less than equal to n, we will calculate the order of p by going at each prime, and by the simple number of divisors formula, for we will multiply each power plus 1. So that will give the answer. Yeah, the solution is correct. Should I explain it on board or it's fine? Okay, great. Yeah. So next problem is dedicated to my friend Abhinav. So it's the problem. So you have to compute the number of divisors of factorial. I guess it's the same. No, the constraints are quite different this time. The numbers are till the range 10 power 8 instead of last time it were 5 lakhs or something. No, this time the numbers are quite great. So how do we do that now?
We just calculate all the primes typical is for.
Okay, then.
Then for each prime we calculate.
Yeah, but the test cases are 5000 and numbers are till 10 power 8. That would take a lot of time. And for calculating order also we need some time.
ऑर्डर कैलकुलेशन और फास्ट हो सकती है,
How? n by p plus n by p square, इससे शॉर्ट क्या करेगा? Like we even don't have enough time कि हम हर प्राइम पे जा भी सकते हो 1 से n तक, उतना भी टाइम नहीं है हमारे पास, तो और तेज़ करना उससे कैसे करेंगे? लाइक हर प्राइम पे हम जाके देख भी नहीं सकते. अगर बहुत तेज़ मान लो O1 भी हो जाता, so still we can't go on every prime, that would only take a lot of time, so how can we calculate? Sorry, क्या? How? Yep. So, but in n there are a lot of prime factors which we can't take care about every time, na? Like n is not co-prime to n minus 1 factorial always, na? So we can't do that. I guess all of you are familiar with the concept of prefix sums, right? Right? Okay. So let me give you one more minute of thinking time, then I'll tell. By the way, all of you have like heard the term about square root decomposition or not? Oh, not right now. Okay, no problem. So let me tell it right now only then. Oh, sorry. Yeah, so what's that? So what we will do there is we will first calculate all the primes by sieve. That's fine. So we will. So the first step would be computing primes. So the second method would be that how do we calculate the order? So one thing we can observe in the above formula of order, that if n is less than p square, then order n in p of p is sorry then order of p is equal to n by p, right? Because all of the other terms will get 0. Right? So we take advantage of this fact. And now what we will do is, first we will calculate, for each prime we will go from 1 to square root n. And we will calculate the order of each prime. Wait a sec, sir. Ouch. There. Right. And then for the primes greater than square root of n, we know that the order of p is n by p only. So we can say that from n by 2, the primes from n by 1, n by 1, the primes from n by 2 to n will have order 1. Right? Similarly, the primes from n by 3 to n by 2 will have order 2. Yeah, the first one is excluded. First ranges. Right? Similarly, for n by I to n by I plus 1 to n by I, the order is I. Right? So we just calculate the primes and then store them in a prefix sum. Right? What is the number of primes till n? Now what we do is we can calculate how many prime numbers are there from n to 1 by n. Right? From prefix sum, so no 1. And we just do 2 to the power the number of primes found, because the order is 1, right? So the number of factors is 2 power. So it will contribute 2 into 2 in number of factors, right? By the formula of number of factors in prime factorization. Similarly, from n by 3 to n by 2, let's say the answer comes x2. So 3 power, we will multiply x power 3 to n our answer, 3 power x2, sorry. So similarly, if we do this process till from I1 to root n, then we will be able to calculate the contribution of prime numbers from root n to n. And for 1 to root n, we can calculate that by brute force, like by going on each prime and calculating the order and multiplying order plus 1. So this problem is clear? So I guess you should implement it, or should I implement right now? Implement कर दो. Okay. एक्चुअली आई हैव सॉल्व्ड इट बिफोर, तो वो कोड दिखाऊं या फिर नया लिखूं अभी स्क्रैच से? छोड़ना है, लिख देता हूँ कोड, लाइक बहुत बेकार लिखता था. Sorry. Sorry. So. Okay. Yeah. Actually, for the code, you have to take care of one more condition, that from n by I to n by I plus 1 to n by I and 1 to root n, your both of the ranges should never overlap. Like, they can overlap on root n in some cases. So you have to take care of that also. कहाँ? Oh, sorry. Thanks. Ouch. Shit. Yes. Not getting into the loop only. फोर को तो जाना चाहिए था. Run. Sorry. अरे सीव कॉल नहीं कर रखा था. कुछ तो कॉल हुआ. गलत आया पर कुछ तो आया. ठीक है, बाद में भेज देता हूँ पढ़ना. ठीक है, अभी लास्ट तो नहीं था यार. ठीक है, बाद में भेजता हूँ कोड में. So next topic is Lucas theorem. So yesterday we talked about calculating NCR mod P, right? If P is very large and N is comparatively small, right? Everyone was there, right? So what if P is small but N is large? What would we do then? Like N is, let's say, of the range 10 power 9 and P is some prime, let's say, of the range 10 power 6, for example. So how do we do it? So Lucas theorem is about that only. So it basically expresses NCR for larger n and larger r in terms of smaller numbers. So what it says is, if we convert, like if we want to compute MCN in modulo P, so it would be same as converting them into base P and multiplying the NCR of respective coefficients. For example, I would show that. Okay. So if you यहाँ कैसे बोलूँ स्टार्टिंग में लगा क्या whatever क्या ऐसे बोल ठीक है ये बेटी ठीक है. Okay, so if you want to compute MCN for larger m and n, all of you are familiar with this symbol, right? Yeah. So if you want to compute MCN mod P, where P is some prime, so here we first convert both m and n to base P. Like we write m as m naught p power 0 plus m1 p power 1 plus m2 p power 2 till mk p power k. Okay, where each mi is less than p, right? Similarly, we do that for n also. So yeah, so now what Lucas theorem says is that MCN mod P is equal to product of MICNI mod P. This is the statement of Lucas theorem. So we don't need to compute n factorial now. We just have to compute the factorials till p only. And we can calculate NCR mod p. So like not lot of much detail is like not lot of problems are there in CPU of this, but like some are. So that's why I told it. So it's only of use when mn are large. So there are like I was only able to find 1 or 2 problems. So you can try, go ahead with it. Yeah, what if like by Lucas theorem you can say like mod p you can compute, but what if p we don't give p, we give let's say x. We have to find mod x where x is square free number. You know what square free numbers are, or let me tell you the definition. Yeah, so basically in the prime factorization of square free numbers, every power is 1 only. So that's what a square free, basically it is not divisible by square of any number. That's what a square free number is. So in prime factorization, each power is 1 only. So what if x is square free? How would we do this? Oh, sorry. Yep. Yeah, so if x is square free, yeah, as Sameep said, we would go ahead with Chinese remainder theorem. So about CRT, as the class would be too long right now, I haven't included that in slides. So, but we will provide you the link later to study that. It basically tells you what is if there are multiple numbers that are co-prime, let's say a0, a1 and an. And we want to find a number x, let's say, such that x mod a0 equal to b0 for some given ans and bi's. So Chinese remainder theorem like gives us a direct formula in ON, I guess. Yeah. In ON we can calculate such a number x such that it gives this for each ai xi mod ai is equal to bi for given ais and bi's. That's what Chinese remainder theorem does. So if we want to compute this, we will just do the prime factorization of x and we will compute mod for each prime, right? And then we will apply Chinese remainder theorem. And it will, the number which we will get basically would give. Here we consider if each ai is prime, then there is only unique x less than the product of each ai. Right. So there exists unique x less than a0, a1 till n if all are co-prime. And x plus k into this number would also satisfy. X plus k into this product would also satisfy all these, right? Because the mod of this number is 0 for every ai. Right. So there is a unique number between 0 and this product which satisfy the condition. So by using the Chinese remainder theorem, we will compute for each prime factor of x, and primes are co-prime to each other, obviously. So we will then compute by Chinese remainder theorem the NCR mod x. I guess a lot of you are not getting it. I'll share the link of CRT in the slides. Maybe you will study, then you will be able to understand. So yeah, that's a problem. That's the same problem. Actually, it's not even square free. There are some other methods to compute also. You can study them online. I'll provide the links later in the slides, okay? From where you can study and solve this problem. This is actually a quite hard one. So thank you, and that's all today from my side. Any doubts in today's session? Please ask. So we concluded here today, and any improvements you would suggest what I would improve in my teaching style? So you can conclude.
So we'll conclude our session here today, and you also have a contest at 2:30 p.m. today. So all the best for it, and I hope you crack it. And other than that, we'll have the classes